Good morning, friends. It is my ninth lecture on the same topic, solutions. And today I am going to teach you the depression in freezing point. So already in previous lecture we covered elevation in boiling point. So before we to start this depression in freezing point, first we have to know the what is meant by freezing point. Yes. What is freezing point? Freezing point. Freezing point. Freezing point means what? So it is the temperature. It is the temperature at which it is the temperature at which vapor pressure of vapor pressure of both solid and liquid components becomes equal. That temperature we call as a freezing point of that particular liquid. Means freezing point is defined as it is the temperature at which the vapor pressure of both the components, that is solid and liquid components, becomes equal. Or in other ways we can also say that it is the temperature at which the solid component and liquid component, both these components are at equilibrium. Both these components are at equilibrium. As these two components are at equilibrium, in this case we say that vapor pressure of liquid and vapor pressure of solid both are same. So in short we can say that freezing point is the temperature at which the vapor pressure of both the components, that is liquid and solid, are identical or becomes equal. That temperature we call as a freezing point of that particular liquid. Now it is about freezing point. Now before freezing point there is one more word, that is depression. It is the depression. So if we consider the freezing point of pure component liquid, that of the solution, then freezing point of liquid is different. And if we dissolve some solute into that solvent, then the freezing point of solution is also different, isn't it? Means the freezing point of solvent and solutions are not equal. They differ from each other. Now if you consider a liquid, any liquid, suppose we call as a solvent, we call that as a solvent. The freezing point of liquid and that of the freezing point of solution prepared by adding non-volatile solute. ह्या लिक्विडमध्ये किंवा सॉल्व्हंटमध्ये नॉन व्होलाटाईल सोल्यूट ॲड केल्यानंतर जे काही सोल्युशन तयार होणार आहे त्या सोल्युशनचा फ्रीजिंग पॉईंट आणि सुरुवातीला असणाऱ्या प्युअर सॉल्व्हंट लिक्विडचा फ्रीजिंग पॉईंट, हे दोन्ही फ्रीजिंग पॉईंट कसे असणार आहेत? वेगवेगळे असणार आहेत. हे काय असणार आहेत? वेगवेगळे असणार आहेत. सो विच वन हॅज, और इफ वी वॉन्ट टू फ्रीज बोथ सायमल्टेनियसली, म्हणजे लिक्विड पण आपण फ्रीज करणार आहे प्युअर सॉल्व्हंट, and suppose solution prepared from that solvent by adding non-volatile solute, if we want to freeze that solution also, then which one freezes first? Either solvent, that is liquid, or a solution. Now for that purpose we have to consider a simple concept, that is the, if you consider the solvent only, okay? If you consider solvent, then in case of solvent, these are suppose solvent molecules, okay? Pure solvent, suppose we consider water, isn't it? Water. Then all the molecules in solvent are of similar type. सगळे मॉलिक्युल्स काय असणार? एकाच प्रकारचे असणार आहेत. सो इफ यू वॉन्ट टू डिक्रीज द टेम्परेचर, ऑफ दॅट सॉल्वंट, देन व्हॉट हॅपन्स? ॲज यू डिक्रीज द टेम्परेचर, thermal energy of system also decreases. Thermal energy decreases because temperature decreases, thermal energy decreases. And as thermal energy decreases, its kinetic energy also decreases or lowers, because kinetic energy is directly proportional to temperature. We know that kinetic energy is directly proportional to temperature. So as you decrease the temperature, automatically indirectly kinetic energy decreases. And as kinetic energy decreases, the motions of molecules motions of molecules becomes more and more slower, and as motions of the molecules becomes more and more slower, so जर मॉलिक्युल्सची मुवमेंट त्या सॉल्व्हंटमध्ये स्लो केली गेली तर देर इज ए मोर चान्सेस और स्कोप दॅट द टू मॉलिक्युल्स कम्स व्हेरी क्लोज टू इच अदर. टू मॉलिक्युल्स जे असणार आहेत रँडमली, these molecules comes very close to each other, in the sense we say that the intermolecular force of attraction is increases, and as intermolecular force of attraction increases, automatically that liquid phase is converts into solid phase. And that particular temperature we call as a freezing point of that liquid. So actually this is the in short description how liquid phase freezes into solid phase, means what happens step by step, isn't it? So this is overall about in case of liquid. It's a pure solvent. If we add a non-volatile solute in this solvent, so जर आपण ह्याच्यामध्ये नॉन व्होलाटाईल सोल्यूट ॲड केलं तर नॉन व्होलाटाईल सोल्यूट ॲड केल्यानंतर आता ह्या केसमध्ये ब्लॅक कलर्समध्ये जे दाखवले आहेत ते सॉल्व्हंटचे मॉलिक्युल्स आहेत. पण आता ह्याच्यामध्ये आपण एक्स्ट्रा नॉन व्होलाटाईल सोल्यूट ॲड केले आणि नॉन व्होलाटाईल सोल्यूट ॲड केलं गेल्यामुळं आता सम ऑफ द सॉल्व्हंट मॉलिक्युल्स आर रिप्लेस्ड बाय सोल्यूट मॉलिक्युल्स. In short, we say that suppose this solvent molecule, instead of that this is solute molecules. Here we say that this is solute molecules, isn't it? So as solid molecules are replaced by solute molecules, then what happens here? If you again decrease the temperature, solutions जर तुम्ही टेम्परेचर डिक्रीज करत गेला तर आता काय होणार आहे, टेम्परेचर जसं कमी कराल तसं इथं देखील थर्मल एनर्जी कमी होणार. थर्मल एनर्जी कमी झाली की कायनेटिक एनर्जी कमी होणार, because as you decrease the temperature kinetic energy slowers. But in this case the intermolecular force of interaction between two solvent molecules, means solvent molecules are very away from each other, they are far away from each other, because in between two solvent molecules there is a solute molecules. आणि solute molecules आल्यामुळं आता इथं जितक्या लवकर इंटरमॉलिक्युलर फोर्स ऑफ इंटरॅक्शन्स मुळे स्ट्रॉंग दोन मॉलिक्युल्समध्ये बॉन्ड तयार होतात, तितक्या लवकर सोल्युशनच्या केसमध्ये हे दोन मॉलिक्युल्स ते एकमेकाच्या क्लोज येणार नाही आहेत. आणि त्याला तेवढं क्लोज आणायचं असेल तर टेम्परेचर जे आहे हे टेम्परेचर सॉल्व्हंटच्या फ्रीजिंग पॉईंटपेक्षा हे टेम्परेचर आणखीन काय करावं लागणार आहे, लोअर करावं लागणार आहे. म्हणजेच इन शॉर्ट आपण ते सांगू शकतो की सॉल्व्हंट आणि सोल्युशन ॲट ए टाइम सायमल्टेनियसली जर इफ वी वॉन्ट टू फ्रीज, then first freezes solvent and after still decreasing temperature it freezes solution. म्हणजे काय सांगता येईल, पहिला सॉल्व्हंट फ्रीज होणार आणि थोड्या वेळानंतर आणखीन टेम्परेचर कमी केल्यानंतर सोल्युशन फ्रीज होणार. सो व्हाय दिस इज सो दिस बिकॉज ऑफ द ऑल अबाउट द इंटरमॉलिक्युलर फोर्स ऑफ इंटरॅक्शन. ठीक आहे. देन नेक्स्ट पॉइंट, इफ यू कन्सिडर same concept can be explained graphically, because in previous lecture I told you that is the all qualitative properties are interrelated with each other, either lowering in vapor pressure, elevation in boiling point, or it may be depression in freezing point or osmotic pressure, and all these qualitative properties are interrelated with each other. Why? Because the one of the most important factor, that is depending factor of the qualitative properties is that is the it depends only on the number of solid particles, not on the nature. त्या सोल्युशनमध्ये असणारे सॉलिड पार्टिकल्सचे नंबर्स किती आहेत ह्याच्यावरती फक्त अवलंबून आहे, नाही त्याच्यामध्ये असणारे सोल्यूट जे आहेत त्या सॉलिड पार्टिकलचं नेचर काय आहे. मग ते ॲटम्सच्या फॉर्ममध्ये, आयॉन्सच्या फॉर्ममध्ये, मॉलिक्युल्सच्या फॉर्ममध्ये, ॲग्रिगेट मॉलिक्युल्स झालेत, मॉलिक्युल्स डिसोसिएट झालेत, ह्याच्याशी काही संबंध नाही आहे. फक्त आणि फक्त किती नंबर्स आहेत सोल्युशनमध्ये त्याच्यावरती अवलंबून असणार आहे. दॅट्स वाय नाउ here again we relate this freezing point to the lowering in vapor pressure. So to how to relate the freezing point to the lowering in vapor pressure, for that purpose just we draw a simple graph showing variation between vapor pressure against temperature. So if you plot a graph showing relation between vapor pressure if you plot a graph showing relation between vapor pressure on y-axis and temperature on x-axis. Now here I want to draw first for solvent, vapor pressure temperature curve for solvent. If I start to draw here this point, in the sense at this point we call as suppose A point. At A point temperature is very high, in the sense more, it is in liquid state, pure solvent. As you decrease the temperature, as you corresponding temperature, suppose this one, as you decrease the temperature, what happens? Vapor pressure of that liquid decreases, because vapor pressure and temperature are directly proportional to each other. If you increase the temperature, vapor pressure increases. If you decrease the temperature, vapor pressure decreases. कारण टेम्परेचर वाढला की दोन मॉलिक्युल्स जे आहेत ते एकमेकापासून सेपरेट होणार, इंटरमॉलिक्युलर बॉन्ड जो आहे किंवा फोर्स जो असणार तो वीक होणार, आणि वीक झाला की ते मॉलिक्युल्स एकमेकापासून सेपरेट होऊन वेपर फेजमध्ये जाण्यासाठी ज्यांना जास्त सोपं जाणार. दॅट्स वाय temperature is more, vapor pressure is also more. If you decrease the temperature, vapor pressure decreases, isn't it? Now this can be shown like this: vapor pressure decreases, isn't it? Vapor pressure decreases. Now as you decrease the temperature, in the sense the vapor pressure of that pure solvent goes on decreases, isn't it? But once some at particular point, suppose at this point say C, at point suppose B, what happens? This liquid is in equilibrium with its solid phase. Liquid phase is in equilibrium with its solid phase, and when liquid phase is in equilibrium with its solid phase, we say that is the freezing point of that particular liquid. That is the definition of freezing point. So what happens at point B? At point B, corresponding temperature is the freezing point of that particular solvent, that is the liquid. After B, again if you want to still decrease the temperature, या बीच्या पुढं परत तुम्ही जर टेम्परेचर कमी केला तर आता ह्या केसमध्ये कर्व जो आहे ए बी कर्व हा पुढे एक्सटेंड असाच होणार नाहीये, कारण का सॉलिड जो आहे, सॉलिडमध्ये ॲग्रिगेशन जे आहेत मॉलिक्युल्सचं ते खूप जास्त झालेलं आहे सॉलिड स्टेटमध्ये बीच्या पुढं होणार आहे, आणि त्यामुळे टेम्परेचर जरी तुम्ही डिक्रीज केला तर व्हेपर प्रेशर जे आहे ते व्हेपर प्रेशरचं डिक्रीज होण्याचं प्रमाण जे आहे ते खूप जास्त असणार आहे. दॅट्स वाय इट इज स्ट्रेट लाईन. वाय? बिकॉज ऑनवर्ड बीच्या खाली जर तुम्ही टेम्परेचर कमी केला तर बीच्या इकडे टेम्परेचर कमी केल्यानंतर हा फेज कोणता आहे? सपोज ए बी, सपोज सी. बी सी कर्व काय इंडिकेट करतो? इट इज इन सॉलिड फेज. ए सी कर्व काय इंडिकेट करतो? इट इज लिक्विड फेज. सो ए बी कर्व इज फॉर प्युअर लिक्विड. बी सी कर्व इट इज फॉर प्युअर सॉलिड स्टेट. And exactly point B, what indicates? It is the freezing point of that particular solvent liquid. It is the freezing point of that particular solvent liquid चा तो काय freezing point आहे, isn't it? Now, so this is the ABC curve for the solvent, isn't it? If you consider a solution, means ह्या solvent मध्ये, ह्या liquid मध्ये आपण आता नॉन व्होलाटाईल सोल्यूट ऍड केलं, आणि नॉन व्होलाटाईल सोल्यूट ऍड केल्यानंतर जे सोल्युशन तयार होणार आहे त्या सोल्युशनचा पण कर्व ह्याच्यामध्येच व्हेपर प्रेशर अगेन्स्ट टेम्परेचर आपल्याला दाखवायचा आहे. तर तो ग्राफ आपण सपोज दुसऱ्या एका लेटरनं सुरू करू आपण, बट वेदर दॅट पॉइंट इज अबाव द ए और बिलो द ए. येस, दॅट पॉइंट इज अबाव द ए और बिलो द ए, बिकॉज सोल्युशन प्रिव्हियस जस्ट इंट्रोडक्शनमध्ये सांगितलंय सॉल्वंटचा व्हेपर प्रेशर हा सोल्युशनपेक्षा जास्त असणार, म्हणजे सोल्युशनचा व्हेपर प्रेशर कमी असणार. सो ऑब्वियसली दॅट पॉइंट इज बिलो द ए. सपोज इट इज L point. And if you decrease the temperature, by the same pattern here also, as you decrease the temperature, vapor pressure of the solution also decreases. See here, vapor pressure of solution also decreases. But remember here, suppose this is LM point. Isn't it? LM point, and this is the, actually here see, with red line I will show you at point B corresponding temperature. This temperature is the freezing point of solvent, so it is represented by T naught F. T naught F is the freezing point of solvent, isn't it? So if you decrease the temperature of solution, its vapor pressure decreases, it reaches temperature T naught F, but at T naught F it does not cross or matches the BC line, which is for solid compound. Why? because it is solution. It is for solution. It is for solution. आणि सोल्युशन असल्यामुळं त्याचा व्हेपर प्रेशर जो आहे तो सॉल्व्हंटपेक्षा कमी आहे, बरोबर आहे. आणि ह्या पॉईंटला म्हणजे बी पॉईंटला तो बी सी या कर्वला क्रॉस झालेला नाही आहे. सो वी कॅन से दॅट बी पॉईंट जो आहे तो टी नॉट एफ इज द फ्रीजिंग पॉईंट ऑफ सॉल्व्हंट, बट टी नॉट एफ इज नॉट द फ्रीजिंग पॉईंट ऑफ सोल्युशन. Not the freezing point of solution. We have to still decrease the temperature to freeze that solution. Solution freeze करण्यासाठी आपल्याला टेम्परेचर काय करावं लागणार आहे, आणखीन कमी करावं लागणार आहे. सो स्टील जस्ट इफ यू डिक्रीज देन इट क्रॉसेस or intersect the line BC, and at this point, suppose it is M point, suppose this is M point, at M point corresponding temperature, that temperature we call as a TF, and that TF is the freezing point of solution. That TF is the freezing point of solution. Now see, AB pure liquid phase, BC pure solid state phase, and LM is the vapor pressure temperature curve for solution, and T naught F is the freezing point of, yes I see over, T naught F is the freezing point of pure liquid, TF is the freezing point of solution, and one more point, that is delta TF, the difference between T naught F and TF, that delta TF is the depression in freezing point. Delta TF is a depression in freezing point, and here delta TF is equal to, how it is, TF and T naught F चा विचार केला तर T naught F is greater than TF. T naught F is greater than TF. Now see here. So delta TF is, T naught F is greater than TF, means freezing point of pure solvent जो आहे तो TF पेक्षा जास्त आहे. ठीक आहे. Now if you consider the relation, it is a mathematical relation, then from thermodynamic studies and from experimental conditions we know that delta TF is proportional directly to small m, molality, isn't it? So delta TF is proportional to n. Okay. Now if we remove the sign, proportionality sign, then it becomes delta TF is equal to KF into M. You call this equation first. Delta TF is equal to KF into N, where the delta TF, depression in freezing point, KF is the molal depression in freezing point. KF is molal depression in FP, freezing point, are also called as a cryoscopic constant. Cryoscopic constant, isn't it? Cryoscopic constant, and where M is the molality. Where M is the molality, isn't it? Molality means concentration of solution is expressed in molal, small m, not molar, because molarity is the temperature dependent, and we are varying temperature here. Molarity is the temperature dependent, and we are studying the temperature factor here. Molarity is temperature independent, isn't it? That's why concentration is taken in molal, small m. So delta TF is equal to KF into M. Now here KF is the cryoscopic constant, and if you want to define that cryoscopic constant KF, just I made simple assumption, that is, if I take small m is equal to 1 molar, if I take small 1 m is equal to 1 molar, म्हणजे कॉन्सन्ट्रेशन सोल्युशन जे तयार केलं त्या सोल्युशनचं कॉन्सन्ट्रेशन जे आहे ते सोल्युशनचं कॉन्सन्ट्रेशन 1 मोलर आहे असं आपण जर अजून केलं तर 1 मोलर कॉन्सन्ट्रेशन असताना स्मॉल एम ची व्हॅल्यू 1 येणार, आणि स्मॉल एम ची व्हॅल्यू जर 1 आली तर इक्वेशन फर्स्ट काय येणार, येस, delta TF, I will take here, delta TF is equal to KF into 1 instead of M1. That is, I will write directly delta TF is equal to KF. Delta TF is equal to KF. So from this equation, one can define KF. What is molar depression in freezing point or cryoscopic constant is defined as, कशाला इक्वल आहे, डेल्टा TF म्हणजेच काय, depression in freezing point. कधी, ज्यावेळेला स्मॉल m ची व्हॅल्यू 1 मोलर असेल त्यावेळेला. So we can define that is the KF is the molar depression in freezing point produced when concentration of solution is 1 molar. When concentration of solution is 1 molar. So Kf, molar depression in freezing point or cryoscopic constant, is nothing but depression in freezing point when concentration of solution is 1 molar. When concentration of solution is 1 molar, isn't it? Now, so this is a definition. Now, if you consider the units of Kf, units of Kf, जर युनिट आपल्याला पाहिजे असेल केएफचं तर केएफचं युनिट पण देता येईल कसं जस्ट रिअरेंज द इक्वेशन फर्स्ट टू गेट केएफ सो केएफ इज इक्वल टू एम ला इकडे ट्रान्सफर केला डेल्टा टी एफ बाय एम delta tf by m. Now here see delta tf is the delta tf depression in freezing point, hence it is the temperature चा scale आहे तो unit देणे temperature चा आहे either degree celsius or kelvin, isn't it? So kelvin or degree celsius divided by small m molality, small m molality, mole per kg. So the expression in mole per kg, mole per kg. So what is unit of kf? It is kelvin kilogram per mole. Kelvin kilogram per mole. It is the unit of, that is the kf. Kelvin kilogram per mole is the unit of kf. That is the cryoscopic constant, isn't it? In the definition of kf, units of kf, isn't it? Now here, or degree Celsius kg per mole also unit. If temperature is taken, degree Celsius kilogram per mole. Degree Celsius kilogram per mole is also unit of cryoscopic constant or molar depression in freezing point, isn't it? Now next point that is we have to study. So this is overall about depression freezing point. Now we are going to study the last point of the concept, that is the application part. What is the application of this depression freezing point or freezing point concept? Application. Applications. If you consider application, one of the most important application, I already told you that the all colligative properties has said same application, that is they are used to determine the molar mass of unknown